Okay, so imagine a car driving along the road. So you're standing 25 meters from the road. So here's my road. The car's traveling really fast this way. So it's closing the distance between you, your observation point, and where he is. So he's going at 180 kilometers an hour. And as he speeds by, you're going to rotate your head to follow. Okay, so as he's really far away, you're not going to turn very quickly, but right in front of you, you're going to turn your head really quickly to try to follow that car. So we want to figure out we've been given the change in the distance of the change in time. You're given this length here. We want to know how fast this is changing when we know the rate of change of this. So we need to relate this distance, which we'll call maybe d. Does it give us a variable here? I think we'll just call that d. Yeah, with our dd. And we need to relate the distance to the angle. So this is similar to the last problem, that we can just say that d over 25, opposite over adjacent, is equal to the slope. Okay. There's our relationship. We've been given dd over dt. The problem is the units here are meters, the units here are kilometers. So we want to do, and I think we want radians per second. So what we're going to have to do is convert that dd over dt into negative 180,000 meters over seconds. There's 3,600 seconds in an hour. So simplifying that, oh, that's going to be hard to simplify. It's going to be 1800 over 36. Okay, so it's going to be 1 negative 50 meters per second. Okay, I think that's right. That times, oh no, so that 200 meters per second, I think. No, I think I had that right. Negative 50 meters per second. Okay, so that's our change in distance over the change in time. I'm going to differentiate this. I'm going to end up with 1 over 25 times dd over dt, which we know the derivative of secant is secant squared times, again, theta changes with time, so we're going to treat that as an embedded function. Plugging all the parts in, I get 1 over 25, negative 50 meters per second. And secant squared, theta, well, I can figure out theta and figure out secant, but I have all the parts here, so I might as well just use secant as hypotenuse over adjacent. So I'm just going to calculate that. That's going to be 625 plus 10,000, so 10,625 square root. Okay, I'm not going to bother simplifying that, but this is going to be my ratio, the hypotenuse over adjacent squared. So secant theta is going to be that times d theta by dt. Okay, and then I can simplify all this. Oh, that looks kind of messy, but looks like things simplify nicely here. That's going to be equal to negative 2, and then that's going to be 625 over 10,625. Okay, so we can simplify that. I'm just going to punch that into a calculator, and that will give us radians per second. So it's going to be negative 2 times 625 divided by 10,625. I'm getting negative 1.2 radians per second, which are negative 0.12 radians per second. Okay, and I just want to double check that. 1800 divided by, yeah, okay, so that seems about right.